Okay, hello everyone, you're most welcome again. My name is Mutanda Samira. Now we are back onto our physics revision series. Okay, now we are going to look at a very good item, and now this one is coming from modern physics. In fact, the mighty modern physics. Okay, there we are. Now we are in for item 017. Please, you can check in the playlist. We have right here from item 001 up to where we are, which is item 017, or which you can simply call item 17 in simple terms. Okay, there we are. And now this item, please, has a very good learning point. How? A lot, in fact. And as far as modern physics is concerned, at least you'll have something to learn in here. Now my humble request is that you should watch the video today and such that you indeed at least pick up something from this video. Then also, please, a simple reminder for whoever has not yet subscribed to the channel, please, in some few days to come, if you have not subscribed, you'll not be able to access this channel, because it will only be available for people who have subscribed. There is a way how YouTube allows us to limit how many people can access the channel, and of course, just to give back to the subscribers on this channel, those who watch when have not subscribed, just know in a few days, even this very week, you will be off, and even if you try to access this channel, it will be no more. So better subscribe such that you're not caught offside. Anyway, thank you. Let's continue. Now I want to show you what you're going to have at the end of this video. Okay, have you ever seen this? All right, good. Now guess what? It's a graph in modern physics. All right, good. And now to look at such a graph, okay, you see, have you ever had a graph about thickness in modern physics? Not really, I guess. So you better keep on this video such that you gain something. Okay, what if when is the very number which appears in your name? You never know. Who knows anyway? Or a resemblance of that kind. Well, I'm not saying that they can set that very item, but maybe a resemblance. Yeah. And it's the reason why we even do numerous examples, such that maybe from those ones you can find 4 or 3 of the items which have the same idea. And now, of course, there you'll be able to get the question answered, and if you're a student, you'll pass, and if you're a teacher, you'll make good results, and hence a good name, or in simple terms, a marketing tool for you. Okay, so this video is simply good for a senior 1, 2, 3, 4 students. If you're in senior 5, please, not really. Okay, so without wasting time, let's proceed. Yeah, once again, we remind you to subscribe to the channel, and we are simply reminding you again that, please, for whoever not subscribe to this channel, you find that by next week you'll not be able to access this channel. Reason, I'm going to call off whoever has not subscribed to this channel. It should remain for only those who have subscribed. After all, they are like 1K plus, and that's enough, I think. Right, so I think let's go there without wasting time. We have item 17. Okay, good. Now there we are. So we have that as our item 17. Get a laser pen here. So they're saying, okay, good. Now they're telling us that during the manufacture of plastic sheets, strontium, which decays, by the way, strontium is a radioactive substance. We have strontium, we have uranium, we have plutonium. There are very many. Okay, so strontium is one of the radioactive substances, or substances which emit radiations. That's what you must know. Okay, good. So strontium, which decays to, all right, good. Let's proceed. Saying during the manufacture of plastic sheets, okay, strontium, which decays to yttrium. Now this one is said as yttrium. Okay, it's said as yttrium. Okay, yttrium, according to the equation below. Now you see that we have strontium, symbol is Sr, plus, okay, some radioactive particle there. Okay, then it will give us what we call yttrium, decays to yttrium. That's what we simply have right here. So now I think that's what we have right away, but I think this one here is meant to be just simple an arrow. Okay, this is meant to be just an arrow. Please take it like that, not necessarily an equal sign like we are taking it to be. So now I have this one here is strontium, Sr, plus a radioactive substance. It will radiate now to give us, now this one, this X here is what we call to strontium decays to yttrium according to the equation below. Okay, so I think let's go there. Now this yttrium here you're seeing, okay, so all right, good. Now we've tried to at least get it corrected, please. Okay, we have tried to at least get it corrected simply. So now they're saying during the manufacture of plastic sheets, strontium which decays to yttrium according to the equation below. Please, this one is said as yttrium. It is yttrium. Now yttrium is an element, by the way, a reductive substance, more like the normal elements you know from your chemistry, but it is simply used to make the, okay, if you're very keen about the LED TVs, LED TV screens, yeah, that's what they use them to, especially those ones which display red color, red LED TV screens. Anyway, that's its use. However, they may not, that's the issue, that isn't the issue we have here. We simply want to see what is really happening here. So okay, now strontium decays to yttrium according to the equation below. This one is yttrium. Now we have strontium is here, now decays to this arrow, we have yttrium is here, and then plus another radioactive substance just right there. Okay, because after a radiation has happened, once a substance decays, it goes to another element. Now that element comes because of, anyway, okay, so when the element decays, it forms another element, but with the release of a certain radioactive particle, which you may not necessarily know. Of course, you have X, which is small a and small b. So during the monitoring process, the following results were obtained. So I think when they were allowing some strontium to pass through a certain sheets, plastic sheets, this is what they got. Like in the thickness of 0.11, they got that 988 counts per second. 0.26, they got 786 counts per second, and now up to the last value right there. So it is in a table format and we have it right there. So let's now go and see this question here. So now they're saying task. Now of course, please, I know some of you, when they talk about a scenario, you think about that length item, very long with very many statements. It's not the case, please. Of course, this one is a short one. So task: as a learner of physics, part A, identify X and explain why it is suitable for detecting thickness of sheets other than any other radiation. Now, if you think you really learned modern physics, what do you think? Which radioactive particle is used to measure thickness? Are you seeing now that? So you need to keep on this video such that you learn something. Part B, if the sheet is folded into 60 thickness and the count rate is registered as 350 counts per second, find the thickness of the sheet. Okay, good. Part C, state any precautions that must be taken while using strontium. Now you really know that strontium is just like any other radioactive substance. And if you have a radioactive substance, you know the control measures as usual. Okay, now here let's start off with part A. We get the reasoning on part A. Let's get the reasoning on part A. So the same part A, we are meant to identify X. Then we have, after identifying X, like say for example, remember X was like this. It had letter A and letter B down. We shall get the letter A, value of letter A and letter B. Now the values we shall get there shall tell us something as far as modern physics is concerned. And if you think you really covered it, then you must be able to at least get this answered. Where I need to be, I'll be posing a question for you. Okay, now with that, let's go back and see what is X. Now of course you look at this. If you can really look at this, we have our X is just right here. So to identify X, we need to get the value of A and the value of B. But how shall we get the value of A? So for example, allow me to erase of this. Okay, how are we going to get the value of A? So simply we're going to say that now we start with this, the 90 plus 90 equals, now this one acts like an equal sign, so it means that 90, which is the same as 90, now we have a plus right here, so we shall maintain it, so a plus A, like that one, the value of A. So solve, you find that you have a 90 plus okay. So now our aim is to get the value of A. So you find that the A plus 90 minus 90 must be equal to 90 minus again 90. So do you really see that this 90 is equal to this 90? So when you sort of find that the A will give us a 0, if you can really see that. Now it means that part of this, we have this one is X, and this A is 0. So let's see how we can find B. B we shall find it from right here. So B we shall add this equals to that. So it will be 38. The arrow means equal sign. 39 plus again B. So what the value of B? If this one comes over this side, you find that will be 38 minus 39 must be equal to B. Please, you can simply solve this and you see which answer you get. You find that there you get the B will be equal to a negative 1. Now simple our X will be 0 and a negative 1. Now I want to challenge you a little bit. Which particle do you think, which reductive particle has that kind of, like that, okay, has this kind of arrangement? You have here 0 and here negative 1. Which one do you think? Which one do you think really has that kind of arrangement? Please be specific here, whereby the mass number is 0 but the atomic number is negative 1. Which one is that? Which one is that, by the way? Think about that. Okay, again, I will give you a clue. Like, think about this. Is it beta particle? Okay. Is it some beta particles, or is it alpha particles? Which one has that? Or is it gamma rays? Now the answer is on D3. Still I see. Now which one suits this arrangement here? Are you seeing? So that's why I've told you you should keep on to this video. Now with that, let's proceed and see how that is answered. Now that's how we get those values, and let's go and see how they are. Okay, simply got. So we start with, okay, that's the equation, or simply the equation needed to be corrected. The equation needed to be corrected really. So this one is meant to be an arrow and this one was meant to be a plus. So you have clarified that in the very start. So that's how we calculated and got the A is 0. Then also calculated and we got in the B as negative 1. Then our X will be identified as what? Okay, whenever you have mass number 0 and atomic number negative 1, then that will be, let's conclude that we say, therefore X is this, hence it is a beta particle. So whenever you see this kind of arrangement here, then that one can be, we can call it a beta particle. Whenever you start an arrangement there. Now of course, once you talk about beta, you must as well go and challenge yourself. How better can you locate the alpha particles? You must again go and challenge yourself. How better can we locate the gamma rays? How can you tell this is a gamma ray? How can you tell this one is an alpha particle? For beta, we notice 0, negative 1, beta. What about the rest? You must be there, this too. You must be knowing what is meant to be done on what particle given to you. So now with that, we have that. But then, listen, to part A, what did they say? They said, part A, they said, identify X and explain why it is suitable for detecting thickness of sheets other than other additions. Now X is beta, but why is beta used to detect thickness of other thickness of sheets? Can be iron sheets. No, iron sheets is too much, but anyway, the papers themselves, a sheet of paper like them, sheets of papers in a rim, sheets of papers in a book, they can as well be measured, or their thickness can be determined using beta particles. But anyway, why beta particles? Now before we go into that, let's go pictorial first of all, and we learn where do these particles come from before we come on to why they are used to measure thickness of sheets of material. Okay, to start with, the story begins with this. Now realize that to get those particles here, those particles come from unstable nucleus. Unstable nucleus is that element. Now unstable nucleus, just imagine if you are in a room, you are just locked up in a room with too much smoke. Of course, just will not be breathing. So that time when you are fighting to move outside, that's how the unstable nucleus acts. Unstable nucleus is here. With it, it wants to just move outside. It wants to escape away. It is not having peace right there. So in the so doing, when that nucleus splits up out of the atom or element, it will give us beta particles, it will give us alpha particles, it will emit alpha particles, and it will also emit gamma particles. Now you have known where those beta particles come from, but the particles have here 3: beta, alpha, gamma. Now they come from the unstable nucleus, and now of course you have them here as gamma, you have them here as beta, and have them here as alpha. You can really see that after nuclear radiation or emission. Now, these three particles are got from the unstable nucleus. Now, but our point of concern is beta particle. Let's, I think, go there. We must know much about a beta particle. Now, they're saying it is a fast electron with mass number 0 and charge -1. You can really see that. We clarified that, of course, our x was 0 and -1. This 0 is the mass number right there. This -1 is the charge they are trying to tell us. Now, of course, what do we know about a beta particle? Of course, this is our case study today. Now, come and look at this. We have the name, the mass, charge, ionization, and range. We must now compare all of them such that in order to understand what beta particles will do, we must compare all of them. So we have the alpha, we have the beta, we have the gamma. Now, what must you know is that they have been arranged in the order of penetration. Alpha penetrates least, followed by beta, then gamma penetrates the highest. Gamma has the highest penetrating power, okay, like that, followed by beta, and lastly alpha. Now let's compare this. Which range does the alpha particles take? Alpha particles they can't penetrate skin. Now just imagine your skin, and these alpha particles can't penetrate it. Just know they are very weak. But then you must then, okay, the beta particles can penetrate 3 millimeters of aluminium. So millimeter, that would be something very small, more like a sheet. Okay, yeah. So that is it. Now the gamma rays, with these ones, they can penetrate hundreds of kilometers in air. Now are you seeing they can even penetrate kilometers? Gamma rays. It means that gamma rays are very, very strong. So gamma rays can penetrate many body. Beta particle can penetrate into skin, but cannot penetrate into body organs like the lungs. It cannot penetrate. Alpha particles, they can't even enter the skin. Okay. So with that, I think I've started noticing something, that as far as these particles are concerned, beta has a low penetrating power to an extent that it can penetrate skin, but it can't penetrate body organs, meaning that if beta particles are allowed onto the front of your stomach, they can't move out the other side. Those are beta particles. Meanwhile, the alpha particles, if they're allowed onto your skin, they can't even enter your skin. That is it. But this stubborn man here, once it's entered into your body, it can easily move out. In fact, it can penetrate. If they are directed into your stomach, they can come out from the back, meaning this is your body. Okay, if they bring them from here, they can easily penetrate through and pass through like that. Those are the gamma rays. They have a high penetrating power. Okay, now next. Anyway, are they risky in any way? Let's see. Are they risky? Alpha particles are not all that risky. Reason? Can't penetrate the outer skin layer, so not risky. Okay, now let's look at this beta. It is moderately risky because with it can penetrate skin. However, penetrate skin but not organs. So with it can penetrate your skin but cannot penetrate the organs like the bones. It cannot, the heart, it cannot. Then what about gamma? With gamma, it penetrates to organs and it has the highest risk. So you must be careful about that anyway. So that is it. Now, of course, you have known that the beta particles can penetrate sheets of paper. Now compare, it can penetrate into your skin, and your skin is very small, more like what you call a sheet. A sheet is any flat surface with a thin thickness or very small thickness. That's what we mean by, okay, a sheet. Now, what if when you look into the uses, don't you think alpha particles have uses? Now look, alpha particles are used in smoke. Okay, smoke detectors. Beta particles are used in making the books you see, because they can penetrate the sheets of paper. Then the gamma rays are used in the radioactive imaging, or what some people call, anyway, I don't know, or is it X-ray? I don't know, but we shall get this into details. So this one can penetrate a sheet of paper. Those are beta particles, while alpha particles, with them, they're used in smoke detectors, or what you can simply call fire alarms. So with that, let's move to the next part. That is, let's go learn about this. Now again, we are proceeding about the beta, alpha, and gamma particles. Before you go to the other work, you must be knowing this. So this alpha is used in smoke alarms. Now what happens is, this one here is the alpha particle, and is radiating energy from here up to this detector here. Now when the energy is moving smoothly from the alpha particle to the detector, to the smoke detector, in fact to the alpha particle detectors here here the alarm will just be silent. Now guess what? What if when, I'll bring this scenario here. What if when, I'll bring this. What if when, okay, now maybe house is burning and some smoke comes. That smoke comes and converges here, collects itself here. Collect itself here. So it means that the particles which will be coming from this side, it means that the particles which will be coming from this side will not be able to pass this level here like this, and will not be reaching this level. And once this one is not detecting the alpha radiations, then the alarm will start now to, okay, an alarm will be switched on and will be allowed to sound hard, and then the people will know that there's maybe fire outbreak in the house. That's the use of the alpha particles. Okay, good. But remember, our aim here is on beta particles. Now, beta particles are used in measuring thickness of a paper. How? By the way, now like in the paper factory, when they're making the books, they will know that maybe one sheet of paper like this, sorry, let me resolve this. In the factory, they really know that maybe this is one sheet of paper, and then they will know that maybe it takes 1 second for beta particles to penetrate into this piece of paper like this. Now they'll put a bunch of papers of unknown number, a bunch of papers, very many of them by the way, a bunch of papers, just like that. Now they will allow these beta particles to come and penetrate this. Then they will count the seconds which it takes for it to pass through. Of course, there will be a beta detector this side, so the time this one takes to pass through, maybe it is 10 seconds. If you are really keen about this, if it is 10 seconds, but we know that 1 second, it takes 1 second for it to penetrate one sheet. It means that 10 seconds will be equivalent to 10 what? Sheets. It means that 10 seconds will be equivalent to 10 what? Sheets. Okay, as simple as that. And now that's how it measures. Okay, reason, the more, or we can even explain here, when the particle is too thin, very many, of course, if it is too thin, like you can see the size here, very small, here is kind of bigger than the other one, and this one is a bit bigger than the other. So it means that beta particles, as they are passing through this thin layer, remember these beta particles here can be absorbed by the surface. So the small surface, very many beta particles will go through. Remember here we have 100% beta, so if you have from 100 you have 75, means that some have been absorbed. Right now, if it has correct thickness here, also 100, but look what we have in the end, 50%. Then when the particle is too thick, maybe a thick book, what happens is it is also 100 here when the story is beginning, but later on you have 25. So it means that when the book is too thick, the beta particles, few of the beta particles will penetrate and the rest will be absorbed in simple terms. That's what I mean. Now the gamma rays are used in medical imaging, like what you call a scan in X-rays. This is the machine, I think, right here. Now what they do here is, before they will first of all inject you with the, okay, a solution containing gamma rays or gamma particles. They will inject into your body and remove into your bloodstream. Then later on, they will come and put you onto this plate here. Maybe those are your legs, these are the hands. So after putting you there, they will enter you into that machine, and this is what you will be in there. Now this machine has got detectors of gamma rays. Now remember, gamma rays are moving into your body. Maybe you have a broken bone, you have cancer. So as the gamma rays are moving into your body, this machine will be able to detect and tell where the fault is, and that's what we're calling medical imaging. Now a point to note here is that beta particles can penetrate into any material. Sorry, the gamma rays can penetrate into any material. Then beta particle can penetrate materials of very small thickness, like a piece of paper. Then the alpha particles cannot penetrate any other material apart from, you see, it can't even penetrate skin. It means that it's a very, it has a low penetrating power in simple terms. Okay, so without wasting time, I think let's get there. Okay, now let's get this written. Okay, there we are. We get this explained with what we have had in the pictures. At least we can get this explained a little bit, a little bit. Let's get there. Okay. Okay, now the saying, beta particles are preferred for use in monitoring process during production of plastic sheets. Now a plastic sheet, you can think of maybe something with a very small thickness, yeah, because they are partially absorbed. Yeah, now you realize that the beta particles are not all that absorbed compared to other particles like alpha and gamma rays in simple terms. So depending on thickness, so it means that the beta particles can penetrate very small thickness. Okay, now when the sheet is thick, more of the beta particles are absorbed. Now we had that in the pictures in terms of percentages. When the sheet is too thick, then beta particles are absorbed. When the sheet is thick, more of the beta particles are absorbed and a few penetrate through, while if the thin beta particle pass through and detected, therefore control system can be adjusted accordingly to produce the sheet of required thickness. Now of course I explained this right here, that maybe if it takes 1 second for a beta particle to pass through a sheet of paper or a sheet of plastic, then they will know that if it takes 100 seconds, those are 100 pieces of those sheets. But what if when it is penetrating, then all of a sudden it takes 2 seconds to pass through? It means that this material here is too thick and therefore is not of a required size. So they will resize it and bring it back until when it takes 1 second for it to penetrate one sheet. That's what they're meaning here, that if you penetrate through, so when the sheet is thick, too thick, then the beta particles are absorbed and if you penetrate through, yeah, okay. While if it is thin, most beta particles pass through and detected, therefore the control system can be adjusted accordingly to produce the sheet of required thickness. I don't know whether that one can make some sense. I've already explained that. So now what about, of course that's about beta, what about alpha particles? Now just know alpha particles can't even penetrate a sheet of paper. So alpha particles are completely absorbed by the sheet irrespective of the thickness and thus can't be used. They can't penetrate anything. They can't even penetrate skin, so they can't penetrate a paper. Therefore, what about gamma? Now with gamma, none of it is absorbed. Everything passes through, and with that we can't use it. So the gamma rays have a high penetrating power and are almost not absorbed even at a higher thickness, so cannot be used. So with the gamma on a piece of paper, it will just go through like that. Okay, so it means that gamma cannot be used. How about the beta, the alpha? Alpha cannot penetrate. Yeah. Now, the reason why we use beta is because when the beta comes, it penetrates, but some of them will be absorbed. So the time taken for the others to be absorbed as the beta is forgetting to pass through is the one they use to detect what time it takes for it to penetrate a sheet of paper, and then they will know how many sheets of paper are there, or if there is an error in the size or the thickness of a paper. Anyway, hope that really makes some bit of sense. Now with that, let's go to part B. What are they saying? So part B, they're saying if the sheet is folded into 6 thickness and count rate is registered at 350 counts per second, find the thickness of the sheet. But remember now, we had this originally, so we had this table. So like they're like asking us that what if when the thickness this time around is 350, remember I have this, what if the thickness is 350? Now remember that once thickness is 323, that are the counts. If the counts per second are 323, that will be the thickness, 0.90 millimeters. It is in millimeters right here. Now if it's 417, it will be 0.73. Not about when it is 350, which value shall we have here? We can't really get it. So it means that you need to draw a graph such that you can detect or look for this right there, and in the graph you're going to plot these values right there. Let's move. So maybe just to clarify here, please, to clarify a little bit, I was trying to explain this for you guys here. Okay, now what we're trying to mean here was, like say for example, in terms of thickness, as far as beta particles are concerned, I think when the paper is too thick, it will take 25% of the beta particles to pass through. Maybe when it is too thick, it takes 4 seconds. When it is not all that correctly thick, maybe it will take 2 seconds, and maybe when it is too thin it takes 1 second. So here we can detect that indeed now we cannot, maybe if you are making a book of this thickness, if say for example we got the count rate and doesn't reach to 4 count rates per second, then we just say the thickness given to us is not correct, and then we shall have to correct that. Anyway, we are on part B, where we have to draw our graph simply. Now with the graph, I'm going to get demarcated. Meanwhile, I'm also getting the values which you are going to plot right here. We have a table, please. We have a table which I showed you right away in the question. So let's see how this can be plotted straight away. Okay. So now to begin with, I'll be giving you value by value. So allow me call the thickness to be T, like that, and the count rates per second, allow me call it this, count rates per second, like this. So there we are. Now realize that as the story is beginning, we have 0.11 versus a 988 counts per second, followed by we have a 0.26 as our graph is being demarcated, a 0.26. okay, then here we have 786 counts per second. That aside, we have 0.37 to 679. Okay, then 0.50 we have, it is 542. Then we have 0.73. Please, I want to get it here for you so that we can plot it together. 0.73, it goes with a 417 right there. So we have a 0.90, it goes with a 323 right there. Now let's start off with the plotting. And the plotting goes that we plot this first of all. Remember, let's label the axis. That's the title, a graph of counts per second against thickness. That is it. So it means that on the horizontal axis, vertical axis, we shall have thickness in millimeters. We have it right there. Then on the vertical axis, we have the counts per second. That is it. Now these are the counts per second. These ones here and these ones here are its thickness right there. Okay. Now let me call off this. Don't write about that table because you're going to use it. Now let's go about the plotting. Now 0.11 on 0.11, we are plotting this. In fact, allow me use this. So we are plotting this 0.11 versus 988, and we shall have it right here. So it is just right here. Reason 0.11, if you study your scale, this is the scale I'm using, and that point is just right there. Now next level, this point here, we shall have it right there, plotted here, and it's the one right there. Then this one shall have it right here, right there. Then this one shall have it right here, right there. Then this one shall have it right here, right there. Then lastly we have this, we shall plot it here. Okay, like that. Now it's all about understanding your scale. For me, I use the scale of 100 here. I don't know which scale you can use in your graph. Maybe just to explain a little bit is that what you must know, I've erased off since you have already finished plotting. Now what you must know is that from here up here it is 10 small squares. It means that one small square like this is the same as 0.02. Now to know the point you're going to plot, like the first point here was 0.11. Now what you do, you get a 0.11 and divide it by the small square, what one small square has on the horizontal axis, 0.02, and this will simply give you 6 small squares. And now where are those 6 small squares? Let's go and count them. Let's go and count those 6 small squares right here from here. You find that? Okay, 6 small squares from 0, it will be, this is a 5, down 6 is here, and that's why you find that here it is a 5 and a 6 right there. Now how did you get the 988? The 988 is on the vertical axis. Please, what I've calculated here was on the horizontal axis, a sampling how we are plotting. So on the vertical axis, you realize that if you count from here up to here, there are 10 small squares. So each small square has 10. Now you come and say 988 divided by 10. that will give you 998.8. This is same as 99. Now you must count 99 small squares, and this is 1, this is 10, 20, 30, 40, those are small squares, 50, 60, 70, 80, 90. Now 99 from here, so we have 90, so 99 you count one by one, it will be 1. Okay, here we have 95, 96, 97, 98, 99, but correlating with where 0.11 was, that's how we are simply plotting. I hope that really makes some bit of sense. And with that, we have our graph drawn smoothly. So we are now drawing our smooth curve such that we can easily detect the 350 counts per second. Remember, the question was saying that if we have 6 sheets, which are showing a count of 350 counts per second, what will be the thickness? This is a count per second, but they want a thickness. If you have 6 sheets, and for a beta particle to pass through them, it takes 350 counts per second. How many each sheet will be? How much? We want to see that. Now we have our graph already drawn. So means that we have to locate 350 right here. 350, where are you? 350 is just right here. 350 right here. So dotted line from here up to the curve, where it meets the curve, dotted line again downwards. The answer there is what we shall read as the, of course here this is a count per second as you are going to the thickness down. Okay, please, we have in the playlist very many questions about graphical work on modern physics, so you can go there in the playlist and check for the graphical work as far as modern physics is concerned. So from 350, which I have right here, a line goes in that direction, so downwards, all right, up to a certain value right there. So let's see the value right here defined for you. So the value will simply be that we have read it for you, or you can also try plotting and you see. Please, some of these questions you can pause the video and also you try out and you see what may come up later on. Now the thickness for the 6 sheets is 0.86. this is in millimeters. Of course, you can really see here we have it in millimeters right there. Now what does it mean? It means that okay, let's give a conclusion here. So that from the graph, the thickness of 6 sheets equals to 0.86 millimeters. So 6 sheets have that. Not about 1 sheet. So 6 sheets are equal to that. What about 1 sheet? We'll have to divide. So 1 sheet will be given by, you divide this by 6, then therefore we shall have 1 sheet as. So we shall have 1 sheet as, when you divide here, we shall have a 0.14 millimeters. That's what 1 sheet will be. Remember, there were 6 sheets which gave us a count of 350. So you come and look at 350, dotted line back there. Then also they can give you a sheet. Can say maybe they were showing maybe the thickness. What will the thickness of 0.6? How many counts will correlate with the thickness of 0.6? You also draw a line back here and you read the value on this. So it is a vice versa if they have really asked for that. So with that, let's conclude. We say, so we said therefore the thickness of 1 sheet is 0.156. okay, by the way, this is meant to be 0.14. This answer we have right here, it is a typing error here. I think it is meant to be 0.14 millimeters. That's why I always tell you to read the question to watch the video up to the end, because we always make some changes a little bit. So I hope that Yadiel has made the point a bit clear. Now let's go and see part C. Now maybe I'll just remind you with part C. Part C said, let's go to part C. Part C said, state any precautions that must be taken while using strontium. So the precautions you can use while using strontium are the ones there. So the precautions we can take while using strontium, they are the ones we have right there. And with these ones here, please, they are the very ones like the ones we take when handling any radioactive substance. Of course, strontium is among them. To begin with, so we say people working with strontium should put on protective clothing lined with lead. Remember lead. Now, much as we talked about gamma rays, beta, alpha, they cannot penetrate lead, all of them. So lead will be a very good protecting gear. So another one, people working with strontium should handle it using tongs. Yeah, you need a pair of tongs. We have the video in the playlist there explaining this fact, this is the third time even having a question of this kind. Okay. Now, people working with strontium must cover, should cover any wound. Now, strontium produces the beta particles or beta rays, which beta particles can penetrate skin. Now, if they can penetrate skin, what about a skin which has a wound? So it means that they can easily penetrate that skin. Or what if in their gamma rays, they can penetrate that skin and therefore affect you in the long run. So also, people working with strontium should avoid over exposure to radiation is emitted. Yeah, as these radiations here can, in the long run, make you suffer from cancer. Okay. Lastly, people working with strontium should not eat or drink while working with it. Yeah, of course, this is a common rule, not eating in the laboratory, because as you're eating and having the fun, some of these rays can enter into your body and end up damaging it. That marks the end. Please, I simply want to end here by thanking you for always watching. Anyway, goodbye and also nice time. But before the video ends, I'm reminding you, please subscribe, because sometime to come, if you have not subscribed, you will not be able to access the work on this channel. Okay, thank you.